Good day and welcome to our first 2017 Fall Webinar Speaker Series hosted by the International Society for Industrial Ecology. My name is Mai Ichihara and I will be your host for today's webinar titled Open Science and Introduction. The ISIE webinar series invites leading practitioners and researchers from the various subject sections to talk about the latest opportunities and developments in industrial ecology. In today's webinar, we will explore the open science movement which seeks to transform science into a more public enterprise with our speaker, Geoffrey Boulton. Geoffrey Boulton is a Regius Professor of Geology Emeritus at the University of Edinburgh and President of the Committee on Data for Science and Technology. He has made major contributions to our understanding of glaciers and ice sheets and the ways in which they have shaped the landscape over recent geological times. Geoffrey is a champion of open science and has chaired multiple reports on this topic over the last several years. He has also received numerous awards, including the honor of the Office of the Order of the British Empire in 2000 for his services to science and higher education. Before we begin, we would like to remind our listeners that we welcome any questions you might have and will direct them to our speaker towards the end of the talk. Please type questions directly into the Zoom Q&A window throughout the presentation. And with that, we welcome Geoffrey Boulton to the ISIE webinar series. Please note, due to technical difficulties, the first 10 minutes or so of the presentation has been cut off, so the recording will start approximately 10 minutes into Geoffrey's presentation. Thank you.
Routinely examine what you have done. I'm trying to change again. There we are. But the world has changed since Einstein and Feynman. Just over the turn of the millennium, for the first time, the storage of data by digital means exceeded that by analog means. The consequence was a dramatic reduction in cost and an increase of flexibility in the transmission and storage and acquisition of data. And we've seen the enormous explosion of data in the last 20 or so years. It's illustrated by the fact that in 2003, the human genome was sequenced for the first time. It's taken 10 years and cost $4 billion. Now it takes about 2 days and costs less than $1,000. But that digital revolution has had immense implications for the principles that Einstein and Feynman stood for. But first of all, let me just say a little bit about another historical analog for this so-called digital revolution. In the 15th century, this man, Johannes Gutenberg, invented in Europe for the first time movable type printing. The consequence of that was that it dramatically decreased the cost of producing and circulating books. And the assertion that I make here on the right-hand side, that the technologies by which knowledge is acquired, stored, and communicated have always been essential drivers of human, material, and social progress. And the consequence of Gutenberg's invention was a reduction of cost, its availability in a wider market, consequently increased literacy, the spread of formal education, and a sense of personal liberation because of that acquisition of education, enhanced innovation, increases in business innovation, changes in the governance of states, and essentially the European Reformation. That process took the best part of 100 years. Now we have processes in play which, in my view, are analogous to the consequences of the Gutenberg revolution, and it's the digital revolution which is changing the things that we see on the screen in front of us. This is a personal tale that illustrates one of the consequences for doing science. This is me in Antarctica about 4 years ago. Some 30 years before that, together with a friend, I'd published a paper in which we had done an experiment in which we'd had hard-won data points, but no more of 7 of them. Those 7 data points were published, a theory was developed from them. We explained the mode of acquisition of the data very carefully. We evaluated the uncertainties and the errors. It was possible for others to scrutinize what we'd done, the logic of our argument, replicate the data, add to it, change the theory, and it's become quite a significant theory in modern glaciology. 4 years ago, our experiment was to do something which was rather similar, except this time, utilizing modern data acquisition technologies, we had rather than 7 data points, possibly say 7 terabytes of data. And the challenge for us now is to present that data with the same clarity that we were able to do before. In fact, it was published about a year ago, and I am perennially getting messages from colleagues in the same field saying, well, how about this piece of data? How does it relate to the other? I think you've missed a line of data out here, and something of that sort, which illustrates the difficulty of presenting your data in ways which can be challenged as clearly and confidently as they were able to be challenged some 30, 40 years ago and before. One of the consequences of the difficulty of utilizing modern data resources and making them available in ways that they can be scrutinized by others is illustrated here. Over the last 7 or 8 years, we've now had at least 7 or 8, to my knowledge, examples where in particular fields, people have attempted to reproduce data, and sadly, what has happened is that rarely in more than, say, 20% of cases, have those who have attempted to replicate the arguments of papers utilizing the data in those papers, in less than 20% of cases have they succeeded. This is one example here from Nature in 2012, in an area of preclinical oncology, where attempts to replicate some what were regarded as high-value papers succeeded in only about 12% of cases. In other words, 88% of the cases could not be reproduced. So why do we have such low levels of reproducibility? Well, of course, there's misconduct and fraud where people have invented data. There's invalid reasoning, but that's not a crime. But to a large degree, much of it is because there's the data or the metadata, which is the data about data, simply has been inadequate or absent. And that's something that we have to dramatically improve if we're going to be able to build a rigorous basis of science on the data available to us in this digital revolution. I'm trying again to change the slide. It won't go this time, but maybe, yes, there we are. So in a sense, what we've had in recent years is a series of attempts both to identify what needs to be done to correct this pathology of the modern digital world and set out some principles. And one principle contained in the International Accord on Open Data produced by Science International some 2 years ago was that all the data, metadata and code that provides the evidence for a published claim should be concurrently available for scrutiny, and to do otherwise should be regarded as malpractice. And an even more severe injunction comes from the International Union of Crystallographers, which doesn't only refer to data that is the data that supports a publication, a truth claim, but a broad statement to the effect that data, whether publicly or privately funded, scientists should always have the starting goal of divulging fully all the data collected or generated in experiments. One of the rationales for that, of course, is that if that data is made available, even though it may not have led to a published paper, it permits others to tessellate that data with other sources of data to produce new ideas. One of the questions, of course, is the role of journals. Should they require submission of all relevant data? My answer would be yes, they must. Do they have procedures to check data integrity and reproducibility? Or do we rely on post-publication scrutiny by peers? Because most people don't bother to scrutinize most data because most data is related to scientific work that really isn't terribly important. And do we need to develop new standards of repeatability for a data-intensive age? Then, of course, some of you will be aware, most of you will be aware of this concept of fair, so-called fair data. Data must be findable, it must be accessible. You must be able to find where it is. When it's there, you must be able to get your hands on it. Thirdly, it must be interoperable. In other words, different data sets must be, as far as possible, able to be merged together and integrated, and it must be reusable. There is, of course, a realizable aspiration which brings together open data and open access publishing. That is, within the literature, it is a realizable possibility that we, sorry, I've that we could have all the data online and open, all the publications online and open, and for them to interoperate. That would put into the hands of scientists substantial power that currently isn't available. But as I say here, this is a process, not an event. It's something that we need to work on over time. It won't happen overnight, and it certainly won't happen because some important person says it must happen. And then there's a general principle of data sharing, which reflects, in a sense, what the crystallographers have articulated. This is George Bernard Shaw, who's said to have produced this statement that if I have an apple, you have an apple, and we share those, exchange those apples, then you and I will still each have one apple. You have an idea, and I have an idea, and we exchange those ideas, each of us will have two ideas. A powerful concept if we can realize it. But of course, there are major problematic issues. There are limits to data freedom, data accessibility, data openness related to safety and security, privacy and confidentiality. The public-private interface needs to be looked at very carefully in the legal framework too. But crucially, of course, is the incentive, or the incentives to individual scientists and institutions to release their data so that others can effectively use it. Of course, there are some other really quite dramatic opportunities that are there which we largely fail to utilize simply because of the lack of motivation to do so. This is Tim Gowers. Tim was a Fields medalist mathematician, the equivalent of a Nobel Prize. He had an idea about a long unsolved mathematical problem, which he put on his blog site. And he invited others to contribute ideas. And over about a month, something like 27 people produced about 800 substantive contributions and ideas, some of which were discarded quickly, others were picked up and developed. And Tim claims that within a month, not only had they solved the problem that he'd thought of, but actually they'd solved a more complicated and difficult generalization problem. And his comment was, it's like driving a car, whilst normal research is like pushing it. The question at the bottom is the one that I iterated a little before. What stops such processes? The answer is simply the criteria for credit and promotion amongst academics, which you simply must have some effort to. Now let me give you another historical analog equivalent to the Gutenberg analog. This is Antony van Leeuwenhoek, who effectively in the 17th century invented the modern microscope. What he did was to see a universe, a world that had not been seen before, the macroscopic world. And essentially what the modern flood of data does is permit us to observe new patterns in nature and society. New patterns lead to new questions and new answers. The new world that Leeuwenhoek saw is in a sense being replicated to us. We now have a digital microscope that generates so much data that permits us to deduce the existence of patterns of much greater complexity, much greater sophistication than we have seen before. And we must ensure that we exploit that digital microscope. The crucial thing, of course, is that the data generates relationships. It doesn't necessarily generate causality, but relationships are fundamental and have been fundamental in the history of scientific discovery. So what does this data universe look like? Well, there's a great deal of talk and hype about big data, but it's not just the big data, the data that comes through at extraordinarily high velocities, but it's also what I call here biggish data and also small data. Just the amount of data, in whatever volumes and whatever fluxes, has increased enormously. To a degree, those data streams that I've shown there tend to refer to rather restricted phenomena. When we use sensors to explore this phenomenon or that, they tend to be very specific in their role, and they tend to give us things like relatively simple patterns in space and time. But for me at least, the most important aspect is what I call here broad data, in which one takes data from diverse sources which reflect different aspects of the same complex phenomenon, very often has the capacity to generate complex patterns in nature and society. If you like, The vertical axis is what I call the monothematic axis, and the horizontal axis is the polythematic, the interdisciplinary axis. The real problem lies in the fact that it's difficult often to harmonize and extract meaningful features if we have a very great variety of data streams. On the one hand, we have mixed source data, particularly in the social sciences. Then we have high throughput instruments like sequencing devices or large-scale accelerators. It's important to understand that it's the diversity of data which to a large degree puts the greatest power in our hands and of course creates some of the greatest problems. This is an example of the utilization of broad data. It shows the circulation of surface waters in the North Atlantic at one moment in time. There's not a single picture. It represents the integration of data that's been selected from a wide range across the whole of the electromagnetic spectrum, and it shows us pictures that we have never seen before, and therefore poses questions, and hopefully therefore stimulates answers. Another example of broad data is this. It's derived from about 72 million electronic patient records. What it does is to express the probability that if you have one disease, you might also be more susceptible to another disease. It has considerable potential in diagnosis and certainly in the organization and development of health systems. And a crucial lesson that comes from both of these two examples is that the data integration needed to produce such results is achieved by what I call information communities, scientific communities that know what they want and they're determined to get it. But the big game in town is that we can look at complexity and complex systems in ways that we have not been able to do before. 30, 40 years ago, the development of the modern computer in its more developed, advanced form permitted us for the first time to really simulate the behavior of the dynamics of highly coupled systems. This is on the left-hand side is a mosaic showing patterns arising from a 6-component subcoupled system. But the flood and flux of digital data we've had in recent years also permits us now not only to simulate system dynamics, but to characterize them, to characterize complexity, to say what it looks like. And the iteration between those two, the characterization of complexity and the simulation of complexity, puts a powerful new reasoning tool into our hands. And one of the best modern examples that I can think of lies in weather forecasting. Weather forecasts have increased dramatically in the last 10 years, and I'm a sailor, so I can certainly say that's the case. And it's done so simply because we're able to iterate between descriptions of the state of the atmosphere and the ocean surface and the land surface, and satellite and surface monitoring, to take those initial conditions and utilizing the equations of motion to forecast how the atmosphere will evolve. And then we can iterate between the model and data. We can, after say 12 hours, a day, a week, we can go back to the real data, the way in which the real atmosphere has changed, compare the model with reality, and what of course we find is that the model will have diverged from reality. But because we can do this thousands of times and see how much we have to bring back the model to reality for different states of the atmosphere, we can include those empirical evaluations in our predictions, such as to improve them dramatically. And it's a wonderful example of the way in which complex systems can be analyzed, probably for the first time. But there's a problem in the practice of contemporary science in attempting to analyze complex systems which depend on utilizing data from a wide variety of sources. As it says here, in modeling, integrated couple simulation is becoming the norm, where we're taking our understanding of physical, chemical, biological, human processes and coupling them together because of semantic links that we believe exist between them, and undertaking simulations. But when it comes to integrating the data with which we necessarily want to compare models, it's much more difficult. Successful integration tends to occur in relatively narrow silos of limited disciplinary range, such as the oceanographic example I showed you before. And that can be done simply because the way in which the data is compiled is based on common standards. But when we're using data from multiple sources and multiple disciplines, let's say comparing across natural and social sciences, then discovery and integration is a major effort, simply because of the ill-defined standards and ill-defined vocabularies. So the diversity of standards rather than ill-defined standards. If we had shared standardized terminology, it would enable us more widely to integrate the data that's vital in introducing patterns in complex, essentially interdisciplinary systems. And of course, the major global challenges of infectious disease, of climate change, water accessibility, of agricultural production, of international economies, depend upon data integration. It's one of the great challenges of modern science. In principle, we have the tools to do so. In practice, because of our diversity of standards, we're not able to be as effective there as we want to be. As it says at the bottom, implementing standards can be costly, but not implementing standards is even more costly, simply because we're underutilizing the hardware and software technologies that increasingly governments, disciplinary organizations, and other bodies are creating. If we want to utilize the technologies effectively, then we should be integrating our data much more effectively, developing standards to do so. I believe there's a new wave is beginning to form. Over the last decade, we've established by hard work from many groups, principles of open data and fair data, processes of managing data systems, tools for analysis and discovery and citation. And that's largely been done by disciplinary groups who have practical experience in doing those things. There are two big challenges in my view. One of them is embedding these capabilities to utilize the modern data flux across all the disciplines of science rather than those that have so far been successful. And secondly, integrating data so that we can better exploit and address the major cross-disciplinary challenges that modern science has to face. And vocabularies and standards are an absolute key to doing that. It's dull, boring work, but it must be done. In my view, it's going to take the next decade to do it, but we must rise to the challenge. 20 years ago, Tim Berners-Lee articulated this view of what he called the semantic web, say a means whereby data from different sources could be integrated effectively, and rather than by going onto the web to produce the electronic equivalent of paper documents, we actually go to the web and look for real knowledge by being able to semantically integrate the information that's connected and the data that's available there. In order to, in a sense, stimulate the development of a modern version of Tim Berners-Lee's vision, the CODATA Commission on Standards is developing a new collaborative program together with the International Unions of Science to do two things. First of all, to unleash the potential for what I've called here game-changing discoveries across the whole spectrum of research, but secondly and crucially, to enable semantic linking and data integration between disparate disciplinary areas, which, as I say, is vital to the addressing many global challenges. So at this point, we get to open science. All the things I've said hitherto have really been about doing science more efficiently. But if we start to talk about open science, as many have, the key question is open to whom and how? Is it just open to other scientists, as what I've described largely is, or is there a broader public for the openness that within the scientific community we ought to be aspiring to? So what might it mean? Well, open access to research literature, data that is as open as possible, fair data, what I call here a shop window and a repository of research outputs. You might call that simply the web. Fourthly, a culture of open discussion and inquiry in which we share our data more readily. We must get away from the idea that the data is my data I've probably got as much reason for believing it is than most, and that I go to cold and miserable places and work rather hard to get it. But what I should be doing is regarding myself as simply a custodian, a temporary custodian of that data on behalf of the society, the taxpayers that have ultimately paid for it, with my responsibility to ensure that data is as well used as possible, either in my hands or in the hands of someone else better qualified to do so, or someone who will come later and combine with what I have done with that others have done. We've got to get away from the idea that it's my data. And next, and here it becomes crucially important, engaging with society and the economy in the research that we do, in citizen science, in co-design, in transdisciplinary research, and at the interface between research, development, and innovation. Open science is really about learning to talk with, not talking to, others in the co-creation of actionable knowledge. And what it isn't is just open data and open access publishing. As I write here, that's just science talking to itself. So what does open science need from us that are scientists, and indeed from other stakeholders in society? I think increasingly we scientists, and it applies particularly to those in the natural sciences, and I'm one, to be awareness of the social context within which questions are being asked. Because our fellow citizens are asking not questions about this particular piece of biology or that particular rock. They're asking questions, bigger, broader questions. Will the industrial activity that will take place here mean that the water in my area will be polluted? What can we do to improve the life chances of individuals? What can be done to enhance the local health systems? How might we be able to manage the planet in a more sustainable fashion? We also need to adapt to interdisciplinarity, because of course most of the issues I just mentioned are societal issues and are very broad, and they certainly involve the social sciences. And one of the problems that we currently have is the crevasse that exists between many in the natural sciences and many of the social sciences and beyond, who hardly respect each other's methods and hardly respect or understand each other's science, others' findings. We need to ensure that there is sensitivity to and awareness of the ways in which other sorts of scientists work. And the fourth thing we need to do is to be able to utilize the tools and indeed the communications media of the digital revolution to best effect. And with who? Who are the other principal stakeholders? Clearly they're businesses. And universities in particular have been very active in recent years in ensuring that their business links are stronger. But they're policymakers and the practitioners of policy, where we scientists need to understand that simply articulating a scientific view about something doesn't dictate what the policy must be. If you're a policymaker, politician, and let's say you take evidence from a scientist about mechanisms by which the use of drugs might be curtailed or the damage arising from it might be reduced, then as a policymaker, you must bear in mind the ethical stance that individuals in society take and the general societal view. Our view of policy is much more complex, or ought to be more complex than simply that of science. In diplomacy too, between states, it's potentially important. There's an interesting example at the moment of the Mekong River, which flows through 6 countries. Each country takes water from it, pollutes the river in one way or another, but have scientific views about the hydrology of the river, which suits their own particular political priorities. What's happening amongst the scientists from those riverine states of the Mekong is they're getting together to ask the question, can we produce a hydrological scheme for the river, hydrological understanding that we all accept as correct? So we agree on the science and then we argue about the politics. But of course, the most difficult of all are human communities and citizens. And the question is, how does science engage with communities and with citizens? And on the scale, and on different scales too, because all of those all of those issues have a local or a national aspect and also an international and a global aspect. There is a phenomenon called global business in a globalized world. There is global policy. It relates to infectious disease. It relates to climate change. It relates to pollution. There are important diplomatic efforts, which are not just local, but global. And both communities and citizens have an interest in the local and in the global. So what are the priorities for open science? What should they be? Well, I think it's possible to think of scientific knowledge or scientific innovations having two important dimensions. One of them is what I call wide and pervasive implications. Scientific understanding, scientific knowledge, scientific discoveries that pervade or have the potential to pervade an enormous number of areas of human concern. One modern example, very topical example, would be machine learning, which as we understand more and more, we realize is applicable to a much greater range of human activities. And then what I call deep implications, and you might say one of those might be individual energy technologies, nuclear energy and the like. What are the implications of that? And of course it will have pervasive implications, but in reality, the area of concern and concentration of effort is highly focused. And of course, that nexus of those two orthogonal axes, I would say all of it relates to what I think is the fundamental global priority of the present day, and that is the sustainable development and use of the planet, a challenge for all of us. So if that's open science, then what about this idea of open society? And I use as witnesses Thomas Jefferson and Karl Popper. Thomas Jefferson, that the people may acquiesce, they cannot approve of what they do not understand. In other words, democracy fails when governments have knowledge which they utilize and which is not shared by their electorate. If you don't understand what's happening, then how can a democratic voice be articulated in relation to that event? And Karl Popper, in his great book, The Open Society and Its Enemies, an open democratic society cannot be maintained where knowledge is not accessible to all. But there are severe dilemmas in realizing those aspirations and principles. They're not dilemmas to which I have easy answers. Both Popper and Jefferson refer indirectly to the idea that knowledge is a public good. And one thing that is broadly true of public goods is that they are freely available. They're not subject to property rights, and their burdens or their benefits can't be restricted to an individual or a collectivity. However, if you look at the right-hand side of that, then there's an economic dilemma. If public goods have zero price, and if additional knowledge has zero price, no one's going to create it. Companies, private sector, for example, will not do so. The supply of new knowledge will dry up. But there's a dilemma there between articulating the relationship between the public domain of public goods and the private domain of private creativity. And we must be eternally vigilant, ensuring that the balance between those two is maintained in a way that in itself is in the public interest. And then becoming a little veering more effectively into the political domain, the more a society drifts from the truth, the more it will hate those who speak it. And in a post-truth world, we see some of the dramatic divergences that occur between different political views and the animus that they create. And of course, it's in that setting that we increasingly ask the question, what is the role of the scientific voice, which arguably tests its explanations against reality to views and beliefs that have no test in reality? It's interesting that last week, a body called the International Science Council was created from the International Council, ICSU, the International Council of Scientific Unions, and the International Social Science Council. And its strapline is that it will attempt to operate as the global voice for science in an earth in which the scientific voice is many, many confusing voices, but where political voices and territorial voices are relatively strong. We do need a global voice for science. And it also has the strapline that perceives science to be a global public good. So there are big issues there that we need to explore. But let me just go back and make an observation which relates to the material I delivered before. And that is to say, we now live in a digitally networked Earth. Information flows, such as those that are illustrated here, are powerful in ways they have, and instantaneous in ways they have never been before. What sort of system is this digitally networked Earth as a system? If you were a scientist and simply meeting this new planet on your voyage of space exploration, then the fact that this particular planet is digitally networked means that its attributes are fundamentally different from the last planet you saw, which might not have been. So what sort of system is it? What are its properties? How might it evolve? Is it some sort of analog computer? There are some questions, high-level questions that we scientists need to ask, which are not abstruse or arcane. They're not different from the sorts of considerations that I tried to spell out in relation to open science and open society, but part of a spectrum of understanding that we need to put together and to realize this understanding has implications broadly beyond the sources on which they sit. So just to recap, I'd simply say that open data, open access publishing, and open science, those two are vital parts of open science, but they're not enough. And open science is a necessary part of an open society in the modern world. Thanks very much. I've now finished.
All right, great. And I apologize in advance. I am in a building where there's some construction going on, so you may hear some background noise. So thank you, Geoffrey. We will now have a brief Q&A session. And thank you to those who submitted questions during the presentation. As a reminder, if you have questions, please feel free to type them into the Q&A box and I will moderate the discussion. So our first question comes from, let's see, Edgar Hertwich here. Give me one. So he says, thank you very much for an excellent presentation. As industrial ecologists, we work much with industrial data. Usually, non-disclosure agreements are required for this work. In what way, in your view, Geoffrey, can industry become more willing to share data on business issues with broader society? Creating and curating data costs money. Today, we see databases of licensed data which are financed by license fees. Are there any business models for openly sharing data that provide the services of curating data?
Well, Edgar, I mean, those are good questions and difficult questions too. Let me try to address some of the easier bits and then we'll get on to the more difficult bits. So, I mean, as you will know, there are now quite a number of business models which are based on open data. The UK government recently did an analysis of business sectors, and somewhat to its surprise, it concluded that there was an open data sector. And indeed, the opening research data and opening government data in particular were an important part of that. And indeed, opening data from private companies was beginning to be more prevalent. There's a classic example in relation to government data. The Landsat imagery, which has been procured now for over 40 years, is held by the US Geological Survey. Prior to about 20 years ago, that data was made available publicly, but at a price. And annually, I can't remember the precise numbers now, annually they would sell something like 200 or 300 copies of that data. Now, 20 years ago, they decided to make that data freely available, and the consequence is now in every year about 20,000 data sets are distributed. They've then looked at the economic consequences of doing that, and their view is that they're very difficult to capture. They certainly run into the billions, and the pattern of collaboration with US agencies that create and utilize Landsat data with international bodies has increased enormously. In other words, global interaction, global networking, and therefore global trade have developed dramatically. I think one of the things that would be an exciting possibility is if we think of the Internet of Things, whereby enormous quantities of data are now acquired daily by all sorts of devices which can do so at a very low cost. And you ask, if we were able to, let's say in the social sciences, lay our hands on parts of that information, then the amount of information, the amount of understanding about human behavior could be dramatically enhanced, both in specific geographical territories and globally. Now, of course, major companies, retail companies in particular, travel companies, they utilize that Internet of Things, but on a relatively narrow bandwidth. So if you're a retail company, you want to know what people buy, what are their attributes, what are their salaries, who do they link with, and so on. And those are all interesting. But actually, the potential of the Internet of Things to deliver much more profound information about the human behavior on this earth, and that is an important issue when we come to the issue of sustainability, then you can see the dramatic enhancement that there might be in our understanding. And of course, that understanding would then, I've no doubt, be fed back into the way in which companies operate commercially. And I think the crucial issue is the extent to which your company believes that it could benefit from openness. Companies that are confident and effective very often believe that if they can stimulate an atmosphere of openness, then because they're very competitive, they will win over their competitors. Of course, there are areas, I mean, if you're an aerospace company designing your next engine, which you hope will take over the market in 15 years' time, the last thing you can afford is to be open. So I think it's a very complex pattern at the moment. And what I would like to understand more, and the title of your organization I think is crucial here, is what does the data ecology look like across the public-private boundary? I've been arguing in a sense for the public data ecology, which is really where scientific funding comes from. And there's a private data ecology which looks rather different, but they do interact at the boundary. And I think it would be good if we were able to explore across that boundary and think about the way in which the whole system is moving and changing. I think, however, there are also some areas where the public interest requires openness. I mean, you might remember that awful incident in Bhopal several years ago when a distinguished American chemical company, there was an explosion, and the consequences were appalling beyond belief in that local community. My view is that the safety case for any company or industry where there is potential danger for the regional population should be available for open accessibility. And I think there are a whole series of areas of that sort where open information is required. In the economy, as you know, I mean, the fundamental tenet of market economy is that markets work most efficiently in distributing and allocating resources where there is a balance of information across the market between buyers and sellers. If buyers know a great deal and sellers know very little, then they're dramatically disadvantaged. And the efficiency of the market as a distributor and allocator of resourcing is very dramatically reduced. So I think there are some very big high-level questions, and then some very detailed questions. There's, for example, an OECD report which CODATA contributed to on business models for data, which went both into the private domain and the public domain. So I think there is a real need for a dialogue on this issue, the sort of thing your organization might well want to promote.
Okay, Geoffrey, we have time for one last question. And the question comes from Rick Lupton, and he asks, how can we encourage researchers to publish their research code open source? Should it be peer-reviewed alongside journal articles?
Well, I think that several things. For example, the accord, the Open Data Accord that I referred to, produced by Science International some 2 years ago, did set out a series of responsibilities. And one of the responsibilities was for scientists, particularly scientists that were funded through the public purse. And that is that they have a responsibility to make their findings available. And that includes the data which they acquire. Now, scientists on the whole don't like normative statements like people should for reasons of principle. And so, and in a sense, that's the exhortatory part. It's the part that says you should be a good boy or a good girl. The other part, of course, is the stick and the carrot. One of the carrots is that much of the analysis done in recent years about the impact of data publishing suggests that if you have good data and you publish it, others use it and cite it. And of course, as an experimental scientist, I would say that for me, the data is the essence. The published paper is merely the advertisement. And the real creativity isn't in writing the paper, it's actually deciding what data to acquire. Because a cunning and clever choice of an experiment or a mode of data acquisition in order that it should reveal something that has hitherto been unknown about nature or society, that's the critical step of creativity. And what we should do is reward that. And as I say, the citation rates for such things are significantly higher than the mere paper that comes from the first time the thing is described in print. There is a carrot, of course there's a stick, and the stick is increasingly being conceived of as being well wielded by funders of science, and that is that if you don't demonstrate that you've published your data and you've got a data release plan, then we won't fund you next time around. But the real carrot, the big carrot, is that if you've got some domains of science, and the ones that come to mind easily are crystallography, bioinformatics, many areas of physics, linguistics. Those are areas that have utilized the data resources that are currently available, have developed sharing protocols, and the benefits that have come to the science they do are really quite extraordinary. And I think that peer persuasion, one group of scientists saying, look, do it the way we do it, because the benefits to you as a scientist and your science in the whole are very substantial. I think that's one of the principal carrots in the business. And indeed, in 2 weeks' time at the Royal Society in London, we're having a meeting involving disciplinary groups that have really exploited their data to a very great degree. And to some degree, they're there to persuade others who haven't yet done that this is the way to go. And of course, institutions increasingly see open data and its exploitation as vital for their future. A few years ago, they simply saw the demands for openness and fair data as a cost, and some of them still do. But the cleverer ones amongst them realize that in the long term, it's for their benefit.
All right, well, that concludes the talk on open science. Geoffrey, thank you for joining us today. And to view a recording of this webinar, please visit the member portal on the ISIE website. And be sure to register for our next webinar on November 10th for a discussion on OpenLCA tools and trends with Chris Mutel and Andreas Serath. Thank you so much, everyone.